some reason.
Happy birthday, Michael.
Thank you. It's not today, though.
Are we going to sing happy birthday anyway, or can I start talking?
But you do realise it's actually not today.
So when is it, Michael?
Never you mind. It's not today.
I didn't ask how many there were.
It's Sunday.
It's Sunday. Sonia told me it's today. Sorry.
No, it's Sunday, and I'll be
okay.
magic number 43.
Yep, I know.
So thank you, Thomas.
Sorry, Sonia told me this morning that it's your birthday today. So,
No, it was close, but no. Hang on. Today is the. Let me just make sure I got the date right. It is Sunday. It's the 24th.
Okay, good.
Before you get started, and since you're here, Thomas, I got just a completely unrelated note. I got the Blakers problems to proofread last night.
Yep.
So they'll be released soon. I'm not sure if you were planning on doing your usual Blakers problems.
Oh yeah, of course we can. Yeah.
They should be released very soon. I've just got to proofread them over the weekend. So anyway, back to you, Michael.
Yeah, well, just make sure, Thomas, you don't have too many people in your Blakers party. This morning I was lecturing Brazil on super spreaders, so you can't have too many people in one place. Anyway, let's get started before I get distracted in any other ways. Thank you all for coming. So this will be kind of a tutorial. This is actually the last lecture in my 4th year unit at UWA, and we've got a few extra people joining just because, I don't know, they're interested in some of this. The material is not all, most of it, almost all of it is not new, but for many of you, you wouldn't have seen it. Some of you, I can see Michael McCulloch's there, will have seen every single bit of it, and I'm not going to be giving you anything new. So you're quite welcome to tune out from the very start. This is recorded, so it will be going online for the 4th year unit in the UWA teaching system. So if you want to talk about Blakers competition problems, Michael, you might want to keep that till after. And if you have any questions throughout, just either shout out, raise your hand. I probably won't see that, but I've got the chat open so I can see if you want to just say something in the chat. So without further ado, this is, in a nutshell, what we're doing is taking a dynamical system, we are measuring a single time series in that dynamical system, and then we're using that to try to reconstruct the dynamics. There's an established way of doing that, and we are taking an alternative route where instead of following that standard path, we build a network of state transitions, which looks kind of like a Markov state process, and use that to infer properties of the dynamics. So that's the potted summary of everything else that follows. And I probably have to return focus to that. Yeah. So just for some initial formalism, and this is mainly for the purposes of the unit that this is feeding into. Throughout the last 10, 11 weeks of the unit, we've gone through this material, and now this is where it all kind of comes together. So dynamical system, we have some object M which we're acting, which we're moving about. This is our set of states. We have some time process, and we have some evolution, some dynamics, phi, which is acting on a subset of these things. So T is time, M is space, and we have this operator phi tz, which moves points forward in that space. Maybe backwards as well, but not necessarily. And all that we require is that everything behaves as we expect it to, so that if we move forward distance 0, then we don't go anywhere. If we move forward distance t and then s in time, then it's the same thing as moving forward t and then moving forward s. Okay? That's basically all that's the framework that we're working from. And then we make our measurements. So the Z here is our state, and the phi t of Z's is our trajectory of that state. So phi t of some initial point Z naught here is our trajectory. So these sets of things here is what is the underlying trajectory which we're observing. We're observing it through a measurement function. Right? And although it doesn't need to be, we're just going to restrict our attention to the case where the measurement function is a scalar. And the other thing, of course, because it is an experiment, because we are actually measuring it on a computer, we don't get to apply the measurement function all the time. We only get to apply the measurement function for some discrete, countable, and probably uniform set of times. Right? So that gives us a time series which we've extracted via the measurement function from the higher dimensional dynamical system. Okay? So that's everything that's in the background. And the way to solve this problem, and so the problem now is, given this set of states, the time series xi, how do we get back the thing that we started with, this dynamical system? And in particular, what we probably most care about is the evolution operator, or something that's equivalent to the evolution operator. And we may also care about the asymptotic states of a trajectory, so the attractor of the system. So how do we get these things back when all we've got is a time series? And I didn't turn off my email alert. That's going to annoy Dave if he ever watches this, so I'll do that quickly. Okay. So the solution to this problem is now almost 40 years old. And the solution basically says, well, I can take that time series, those states, these are scalars here, the xi's, I can turn them into a sequence of vectors by just taking lagged versions of them, so xi plus 1 up to xi plus m minus 1, so a vector of length m. And the sequences of those vectors is equivalent in a strictly defined sense, that is the dynamics are diffeomorphic, equivalent to the dynamics of the original system, the original dynamical system we started with. And the reason this works, well, Tarkin's embedding theorem guarantees this works almost always. And first of all, there's cases when it won't work if you are viewing the dynamical system in a bad way. But if you happen to have one of these non-generic views of the dynamical system, then a small perturbation to that will give you something for which it does work. So it's going to work almost always in that sense. And the reason, and what we need to do to guarantee it works is do two sorts of things. First of all, there's kind of arguments related to ensuring that the dimension here, m, is large enough that the set of points that we get, these vectors v, have the space they need to topologically be the right object. Right? So there's kind of a topological argument here about the embedding. And the other thing is, to get the dynamics, well, one way to think about that is what we're doing here, at least if it's a finite order dynamical system coming from a set of ordinary differential equations, then getting the state is equivalent to getting a single variable from that state and its m minus 1th derivatives, right? So we could, if we have the value of x dot, x double dot, all the way down to x with m minus 1 dots on top of it, then those things give us all we need to know the state of the whole system. And numerically, the information we need to get all those derivatives, well, if we're just doing Euler differentiation, to get the first derivative, then we just need 2 adjacent states. To get the second derivative, we'll need 3 adjacent states, and so on and so on and so on. So one way of thinking about this process is by having this vector of length m, we've got enough derivatives to get back the differential equations that are generating the system in the first place. Okay, and so there's a few slight extensions to this that say that you can do the same thing if you have a fractal attractor. So that's the solution. That's how nonlinear time series deals with the problem and has dealt with it since the 1980s. There is a slight complication here in that this is a theorem in mathematics, and it says conditions under which you can guarantee this works, but it doesn't necessarily tell you that it may be better to have a different step between the different components, a higher lag between the components, and it doesn't, apart from telling you that m has to be at least, or at most twice the dimension plus one of the manifold that's being reconstructed, it doesn't tell you how to estimate that m, and it doesn't tell you what the best choice of lag between the components is. So when we're doing this process in practice, we have two issues. One is we have a lag between the components, because if we had dealing with a sample time series and it's very, very highly sampled, then taking xt, xt minus 1, xt minus 2 is not going to be the best thing to do, because those individual components don't give you very much independent information. It may be better to take a larger lag. And so in the practical situation, we have an issue with estimating the best lag, and also because we don't know the dimension d and we don't know the embedding dimension m before we do the embedding, we have to have some way of estimating the embedding dimension before we use the embedding dimension. And so this is the subject of nonlinear time series analysis, and there's methods, all of them entirely or almost entirely ad hoc, to estimate both the lag tau and the embedding dimension m. I'm not going to talk about them here. There's plenty of references for it. There's plenty of better references than this one, but that is, at least, you can get that one pretty easily, freely online if you Google it. So what am I going to talk about? One specific aspect of nonlinear time series analysis is what's been called recurrence plots and recurrence quantification analysis. And you guys that are actually doing the unit, we talked about that last week. An easy extension of the idea of a recurrence plot is a recurrence network, because a recurrence plot is a square matrix of ones and zeros. You can take a square matrix of ones and zeros and treat it as an adjacency matrix, and you now have a network. So that's going to be kind of the first step. The second step, we're going to talk about maybe better ways of reconstructing the states rather than doing what recurrence quantification does, and using what are called forbidden sequences to construct what we're going to call ordinal networks. And finally, we'll finish off with some applications of this to data and possible extensions to multi-channel data. And for those of you that were in yesterday's talk, we will eventually get very briefly to what Dave and Deborah have been doing with compression networks, which is another variation on the same thing. So recurrence networks. This goes back even further. I'm now back to the 19th century. And all that we need to know about this is that recurrence is important. If you have a deterministic dynamical system, then you take a state in that system and it's going to come back to where it was before, arbitrarily close, infinitely often. And the point with recurrence quantification is that you look at those times when you come back arbitrarily close in the future, and you use those recurrences to quantify and describe the dynamics of the system. And the reason this works, well, I'll have to get to the pictures on the next slide, but the definition of how we do this in practice for data, we construct the recurrence matrix, the Rij. It's a binary matrix, ones and zeros, and we very simply just say, if so we have a Vi and Vj here, so we've already done the embedding process. We've taken our output of our experiment, our scalar time series, we've constructed a vector time series, the Vi's, and then we look at two of those Vi's, Vi and Vj, and if they are closer than some threshold epsilon, then we say that's a recurrence, and we label the corresponding point in the matrix 1. If it's not, 0. So this definition, the matrix R is symmetric and binary. Of course, you can dream up all sorts of extensions to this. You can use all sorts of different norms on here. There's questions about whether or not you do the embedding process correctly. So the way in which you get the V's from the vector V's from the scalars X, that will affect the whole process. But, and then there's the issue about how you choose epsilon. All those things aside, this then gives you a binary matrix which shows the recurrences in the sense of Poincaré's theorem for a dynamical system. An alternative method, which is usually not so favoured, but was actually the original way it was described when people first started looking at recurrence plots, is to, instead of saying Vi and Vj are a recurrence if they're closer than some distance epsilon, we say that Vi and Vj are close, or we say that Vi and Vj are a recurrence if it's one of the closest k times that points are near to each other. So this is an indicator function in this definition here, and the definition is a bit more complicated. It looks a bit convoluted, but essentially what I'm doing is I'm saying for a point I find the k closest neighbors L and call those, sorry, I find the k closest neighbors J and call those Vi, Vj's the recurrences of Vi. So each point is only going to get k recurrences. Right? So simply, we either treat recurrence as an epsilon ball around a point or k nearest neighbors. The advantage that, well, I will argue the advantage of the k nearest neighbor approach is that it doesn't depend on local deformation of your state space. So if you've got a state space where in some parts you don't have many points, they're spread out a lot because the dynamics is maybe fast, and in other points you have lots of points close together because maybe the dynamics is much slower. If you use the epsilon method, then the epsilon balls in that slow, densely populated area are going to be much fuller, whereas in the sparse area they're going to be much more empty. If you choose a fixed number of neighbors, then you are quantifying nearby states in a way which is robust to that deformation of state space. Why would we want to be robust to such a deformation? Because that's what the embedding theorem, that's all the embedding theorem is guaranteeing us. When we apply Tartan's embedding theorem, we're saying the attractor is reconstructed up to smooth deformation of state space. So we're allowed to stretch state space. So in a way, we would prefer the second definition because it's robust to those changes. But in fact, it turns out both work. Both at theoretical and practical level, both methods work fine. So this is just 4 examples for you. This is, now for those of you doing the unit, these are the pictures which I didn't show you last week because I just was scribbling on the back of a piece of paper instead. But this is essentially 4 different time series, shown vertically rather than horizontally, but 4 different time series starting at 0 and moving forward, not that it matters. 4 different time series of the Russell system with 4 different sets of parameters, 4 different values of the bifurcation parameter. And you can see as you transition from something which is more strongly periodic to something which is more chaotic, these 2 here, for example, you can see that the recurrences become less regular. In the idealized periodic case, you're going to get a recurrence at time intervals separated by the period. So you will see just diagonal lines on the recurrence plot because every period there's a recurrence, and every 2 periods a second one and a third one and so on. When it's chaotic, and if you have a smooth low dimensional chaotic flow where you've got oscillations that are varying and essentially the chaotic dynamics are encapsulated in the first return map, then you're going to get these periods where there's recurrence and almost periodic behavior in a smaller window, but these repeat in a less regular way. So if you are if you are German and you're interested in recurrence plots, you then do lots of different things where you measure the length of these lines, how many lines there are, the distribution of the lines, all sorts of stuff like that, and it's called recurrence quantification analysis. Our view, though, is that, well, this is a square matrix of ones and zeros, so we can think of it like a Laplacian matrix for a network. So we can treat it like the adjacency matrix. So we can treat it just as a matrix of ones and zeros. If there is a one, that means that two nodes, Vi and Vj, are connected. So we can do that with exactly the same thing. So here is those four recurrence matrices treated as adjacency matrices and plotted as networks. Right? So the two more chaotic ones in the middle, there's a lot more going on in the network. The periodic one at 0.411 and the kind of almost periodic one down here, there's a lot less going on. But by plotting it as a network, we have a different set of tools that we can apply to measure stuff. Whereas with recurrence quantification, it's all about measuring these diagonal lines or other geometric line structures in the picture. When we treat it like a network, we can start to think about things like cliques, like the size of loops, motifs, first returns, the diameter of the network, these sorts of network type properties of the network can be used to quantify the structure. So in a kind of ad hoc way, we've taken what people are doing as recurrence quantification, we've produced these pictures. The pictures look kind of neat, kind of pretty. So if it's a pretty picture, there must be something behind it. We apply the network measures to those pretty pictures to try and get properties which we think are going to somehow tell us something about the dynamics. That's kind of the loose, non-mathematical way of thinking about what we're doing. Here's just some more of these things, just to prove to you that they are pretty pictures. This is the Rossler system again. The original time series here. This is the attractor in the original XYZ coordinates, so the chaotic system. The trajectory that I'm plotting is in yellow here, and the red dots are the sampling of that trajectory. I sample the trajectory with those points to create the scalar time series, which is at the top here. From that scalar time series, perform an embedding on that scalar time series to get the network structure. And so the network structure, it's plotted here, obviously a projection from a three-dimensional object to a two-dimensional screen, but the network itself is not strictly necessary. Well, it's not true actually. The network, the adjacency matrix itself does not have a natural Euclidean space associated with it. Or here it actually does because it comes from a distance matrix, but an arbitrary adjacency matrix will not. And the visualization you see here doesn't use the Euclidean location of the points that are the nodes, right? So the large picture that you see is just the adjacency matrix of the network, which is then being represented in 2 dimensions, or rather 3 dimensions, via what is called a spring embedding. So we're using a force relation to try to put nodes that are connected close together and nodes that are not connected far apart. So the layout that you see of this large structure is not actually from the dynamics or from the measurement. It's only just from the connection or not of the nodes. And it looks pretty. It has a lot of fine structure. There's lots of little loops there. It looks kind of like a teapot doily or something. And you've got this sort of pinch going on here, which corresponds exactly to the stretching and folding going on in the original Rossler system. Right? So the fact that you've got these points coming together that are coming to be close that originally aren't close. There's points down here at the pinch that are coming to be close. This is the kind of key mechanic behind what generating the chaos in the Rossler system. It's a question we still haven't quite answered yet about the nature of all these little loops that we see here, whether this is just a sampling issue and a consequence of the patterns that you can see in the sampling here, or whether it is also a deeper property of the self-similarity of the attractor. I'd like answers, but I don't have them yet for that. Here's a second picture. This time, no prizes for guessing the dynamical system. It's the standard Lorentz system with the two lobe butterfly wings. And here, when we represent it as a network doing exactly the same process, we get this kind of, looks to me like a dog's bone, but like a bone that a dog's chewing on. I can't quite explain the big hole in the middle, but if each of these points in the network does correspond to a point in the embedded space and does correspond to a point in the original coordinate system. And what's going on is the two lobes, the two lumps on either end of this network, correspond to the dynamics on the two wings of the attractor. Right, so points that are moving around here correspond to points in sequence moving around one of these two lobes. And the connections through here correspond to points moving through the separatrix here. One thing that I didn't say, which I should have said when I showed you these pictures, these pictures here are different from these pictures here in one very important way. These pictures we constructed with the epsilon ball method, the standard recurrence plot approach to doing all of this. These ones we're using k-nearest neighbors. And we're using k-nearest neighbors in a slightly special way, for no good reason than it seemed to me before I thought about it too much. It seemed to me to be the right way to do it, but it just turned out to be a different way from everyone else. Essentially, we allow each node to contribute a fixed number of edges to the network. Now, the definition that I gave you earlier for k-nearest neighbors, if VI is a near neighbor to VJ, that means that VI wants to connect to VJ. It doesn't necessarily mean that VJ is one of the nearest neighbors. If VI is one of the nearest neighbors of VJ, that doesn't necessarily mean that VJ is one of the nearest neighbors of VI. Right? So VI could have lots of other friends that VJ doesn't have. So we also take care to ensure that although every node is contributing the same fixed number of edges, some nodes will end up with more edges, and we avoid double counting so that the mean degree is exactly twice that number of edges that each node contributes. Okay, that's all technical detail. If that didn't make too much sense for you, just stick with the picture. It's only a slight variation in how we're constructing the networks. So there's the standard Lorentz system, and just to show a third system, this one, just to show that we can do more than just Rossler and Lorentz. Here is True's double scroll circuit, and the original dynamics here in red and yellow, and the network here in blue and maroon, I guess. Structure's more complicated. I'm not going to try to infer where these two lobes are in this particular structure here. It's kind of a bit more twisted up. It's got these little fine scale structures again, even though it's not obvious from the embedding that you have the same kind of patterns due to sampling that we did in the Rossler system earlier on. But we still see these patterns of small cycles in the attractor. Okay, so we have something which is producing interesting pictures. What can we do with this more than just looking at pretty pictures? Well, the first thing that we did is we looked at the small subgraphs within that large network. So we take the network structure and we look at every subgraph of 4 nodes. Okay, so we're looking at patterns of 4 nodes that are connected within that large graph. And we then rank them from which pattern of 4 connected nodes occurs most frequently to which pattern occurs least frequently. So if you're going to connect 4 nodes together, turns out up to symmetry, you can do it in 6 ways. Trust me. If you don't trust me, get a beer mat and start drawing patterns of 4 nodes. That's it. And so on the left here, we have the most frequent one through to on the right, the least frequent pattern for each of, 7 different types of dynamics. Okay, so we're just feeding in either a periodic dynamical system, a chaotic dynamic system, a hyperchaotic system. So here we have 2 positive Lyapunov exponents in a larger dimension, a periodic flow with noise added to it now. So the original first periodic flow here has only integration noise and nothing else. This one has got observation noise, so it's kind of fuzzed up a lot more. And chaotic or hyperchaotic maps and pure noise process. And we tried this for a bunch of different things. It's all in the paper from, 12 years ago now. We tried this for a bunch of different things, and then we counted up how many of each of these 6 subgraphs we see for each of these types of flow, put them in order, and we see, lo and behold, the sequence of hieroglyphics changes depending on the nature of the dynamics. So, big deal. We can tell the difference between a chaotic system and a periodic system by taking a long trajectory, embedding it, transforming it to a network, counting up all the motifs in it, and ordering those motifs. We could have done the same thing just by looking at the time series. But the important thing is not that we have some magical diagnostic to differentiate these things with the motifs. The important thing is that the networks are preserving certain structures within the dynamics, and we can understand these orderings because which orders occur, which patterns occur more frequently or less frequently actually depends in kind of interesting ways on the nature of the underlying attractor. Just have to flip forward to see if I've got that on the next slide or not. No, I don't. Okay, so for example, if you just take this this arrow motif here, right? So what this is saying is I've got 4 nodes connected together. One of those nodes, the one at the head of the arrow, has got 3 things close to it. But each of those other 3 things is not close to anything apart from the head. Now, if you imagine 3 points in a line, the middle point can be close to the left and the right point. Right, so that could explain, here's your middle point, there's my left point on one edge of the arrowhead and my right point on the other edge of the arrowhead. So those 3 things are all connected in a line. Now I have to place this 4th point, the tail of the arrow, somewhere where it's close to the point in the middle, but not close to either of these other 2. That's just not possible if I only have 1 dimension. Right? If I want to arrange 4 points on a line, and I think first of all of 3 of them, that point in the middle has to be close to the 4th point. If I want to get this particular motif where I've got 1 point close to 3 things that are not close to each other, then I need more than 1 dimension. So you see, for example, that means that when I've got a periodic flow which is strictly 1-dimensional, this pattern occurs very infrequently. The other thing I should mention, which is in the paper, is that the number of these motifs from least frequent to most frequent is, I think, 2 orders of magnitude. So I'm not talking about counting these things up and finding 5,002 of these and 5,010 of these. I'm talking about there's 5 of these and 5,000 of these. Right? There's a lot more than, and there's a lot fewer of these ones that don't occur. So it's robust, and we can start to try and understand what's going on in terms of the dynamics. The other question that we would like to ask about this, since these pictures look pretty, and since we can see there's some of the structure of the original system being preserved in these pretty pictures, do we have all of the structure of the original dynamics? With embedding, when I apply Tarkin's embedding theorem and go from a scalar time series to this embedded object with these delay vectors, that embedded object is provably diffeomorphic to the dynamics of the original dynamical system. Right? They are equivalent. All the information of one is there in the other. do we have the same thing with these networks? So the way you would answer that question is to say, can I take the network and go backwards? If I give you just the network, can you reconstruct the time series? Okay, and that's what we're doing here. So on the top panel is my original system in the original coordinate system. I then take a scalar measurement from that original coordinate system. I then embed that, I construct a network, and I then throw away all that information and just look at that network. I take that network and I use that network in a process which I'm not going to describe in detail, but I use that network to reconstruct a time series. Having reconstructed that time series, I then check whether or not it's the same type of object by embedding that reconstructed time series. So on the bottom here is an object that I've retrieved from the network alone, whereas on the top here is the object that I started with. And so you can see they're exactly the same. When I say exactly the same, I mean the periodic orbit here is a periodic orbit here. The thing that's that period, this is actually very close to, but not exactly on the period 6 orbit. As you can see, there's stuff going on here because we kind of missed a little bit. And we've got a periodic orbit, which again, because stuff is getting close in ways which we weren't able to cope with, it didn't quite manage to do it here. We've got 2 lobes over here in the original Lorentz system. We've got a rather less attractive, but still 2-lobe chaotic time series here. And similarly with the Russell system, we've got stretching and folding in the original coordinate system. And although it's not clear from this picture, there is stretching and folding also going on in this reconstruction. So briefly, what is this reconstruction that we're doing? So Yoshito Hirata, reference 8 here, showed that if you start with a recurrence matrix, you can reconstruct something equivalent to the original system only if you've got distances. Right? So you need all the distances, and then you can no, that's not right. He started from the recurrence plot. What's written there is not quite correct. From a epsilon ball nearest neighbors recurrence plot, you could reconstruct the original system with some additional information. Notably, with the recurrence plot, you have the time ordering of the points in that matrix. With the network, although it's the same matrix, when I plot the network here, I'm not saying which points, what is the order in which the points occur. Right, so we need to also, to make this reconstruction work, we also need to label each of these nodes with their temporal order. So with the temporal, and we show that with the temporal order and the network structure, we were able to do something like what Yoshito did for the K nearest neighbor recurrence network, which we're looking at on these slides here. Right, so it's a constructive proof that relies on saying, well, this point is close to this other point, so the time series points have to be close together, and then we try and fit all the other time series points in a way so that they look close together, and then we just smooth stuff out to try and make it look, without changing the ordering, we smooth stuff out to try and make it look more like the original coordinates. Okay, so that's kind of neat because it tells us that even though these properties that we're measuring with these motifs, which was enough for PNAS, these properties that we're measuring with the motifs are kind of a trivial deduction because we're only really showing that chaos and periodic are different. The network nonetheless has all of the information of the embedding. So anything else that you could reasonably hope to get out of an embedding, Lyapunov exponents, correlation dimension, evolution operator, etc., all these things we can get from the network in some way as well because the information is there. Okay, that's cool. When I first started talking about this, though, Gary, who I just check whether he's on here, I don't think he will be. So when I first talked about, I first started doing this, I was talking to Gary Froyland, and he pointed out rather obviously that these networks that I get depend on the length of the time series. And that's kind of obvious, right? Every point in the time series is a point on the network. But what that means is, although I'm talking about the network having all of the information to reconstruct the system, the network itself is not an invariant, right? The network is growing as the time series grows. Whereas with Tarkin's theorem, when you do a reconstruction and embedding, if you have a longer time series, you're just filling out more points in that attractor. You're getting a better estimate of the attractor. Here, with the network, we're getting a bigger and bigger and bigger network. So something kind of funny is going on. And also, the other thing that's kind of funny is that although we can understand this in terms of the embedding dimension, my chaotic flow, it's a sampling of a flow. So really it's a map. So the way in which I'm distinguishing between maps and flows here is kind of an artificial consequence of what I'm starting with, even though all of them are sampled systems. So that kind of got us thinking again. And we thought about maybe a different way of representing the information in the system as a network. So the networks I've talked about so far, built from recurrence matrices, the networks I've talked about so far, the nodes are states and the connections are if those states are close in space. Right, so nodes on the network are close together because they were close together in the embedding space. Dynamics is not explicitly there. Right? When we did this reconstruction process, we had to bolt on the dynamics by saying we're going to label each point with the time sequence. Right? So the invariants of the system are there somewhere, but the dynamics is not there. We have to bolt that on to get the dynamics in the network. So maybe a different way to think about it would be if we can reconstruct a network where the nodes in the network represent states or regions of state space, and the connections between them tell us something about the dynamics, the temporal ordering of what's going on. Okay, so this is where we start with the idea of forbidden sequences. So here is a straight line. Let's think for a moment about the simplest chaotic dynamical system that we look at, the logistic map. That's the logistic map. If we apply the logistic map twice, we get that. Apply it 3 times, we get that. And I've forgotten how many, and yeah. So we apply it 3 times, we get that. And what we notice in those, well, we have 4 iterates here. We have X, the original state. We have the single hump map, which is the first iterate of the logistic map on that state. And I apologize, Thomas, I am using red, green, and blue, so I'm being as offensive as possible to anyone that's colorblind. But you can just count the bumps, right? So the one with no bumps is X, the one with 1 bump is f of X, the one with 2 bumps is f squared of X, the one with 4 bumps is f cubed. Different regions of the state space, the interval 0, 1, these 4 values occur in different orders. Down here between 0 and a bit, we've got X is smaller than f of X, which is smaller than f of X, which is smaller than f of X. And I'm just scanning through quickly. I don't see where the opposite is true. But in another region here, this region here, for example, about 0.3, X is the smallest. The second smallest is f of X. The third smallest is f of X. And the largest is f of X. Right? So depending on my value of X, the successive iterates of the map occur in a different order. What does that mean in terms of a time series? In terms of a time series, that means that x of t plus 1, x of t plus 2, x of t plus 3, if I take those 4 points and just look at the magnitude ordering of them, that's going to change as I move along my time series. Why is that interesting? Well, it's interesting because if I then take each of those regions and label them here x of t as intervals, I can associate with each of those intervals a permutation pi I, and there's a couple of different ways of labeling this. I do this in a way which apparently is counterintuitive to the rest of the world, but you can either fit, in this case, oh, I shouldn't stop touching that. In this case, 4321 means that the x of t is the fourth largest, x of t plus 1 is the third largest, x of t plus 2 is the second largest, and x of t plus 3 is the largest. I can also look at the probability of being in the interval, right? So these are the, if I take a long time series and I look at how frequently I am in the interval 0 to 0.071, which corresponds to how frequently I'm getting the permutation 4321, the frequency with which I appear in that interval is actually the measure on that interval of the system. And the other thing that we see, which is interesting, is that some of these intervals occur twice. So the interval between 1 and 1.33, this little, the second white band here, so I hope you can see, I've got the pointer over it, and this other interval here, this bigger white band at 0.2, the ordering is actually the same. Big deal? Well, it's a big deal because if I'm thinking of permutations of 4321, there's 4 factorial of them. But here I've only got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. Only 12 of them actually occur. Whereas I was expecting, what, 4 times 3 is 12, 24, is that right? Yeah, so a lot of them don't occur. There are these forbidden sequences. Right, so but if I had started with just random numbers, I would not see forbidden sequences. And I would certainly not see sequences occurring with these definite probabilities that are not directly proportional to the length of the interval. Well, that could happen if I choose a particularly interesting noise process, but I definitely wouldn't see particular patterns not occurring. So this is another signature of the fact that I'm starting with a deterministic system. Because the system is deterministic and obeying some rules, different patterns of symbols occur and others don't occur. And this kind of, this is stuff that, so this, I should say this picture that I'm showing here, I borrowed from, oh, I didn't reference Jose's paper, that's very bad of me. I borrowed this from a paper on permutation entropy by Amigo and colleagues. I just think it's a fantastic way of illustrating it. But another way of thinking about it is what we're doing here is we're taking state space and we're partitioning it up into wedges. Each wedge, the boundary of that wedge is defined by when there's a tie amongst some of these things in that permutation sequence. And we're then looking at, we're going to associate with each of those wedges, with each of that permutation, a node on the network, and look at transitions between those nodes. So that's our new scheme to construct what we're going to call an ordinal network. Okay, so this comes out of the idea that those T-cozy doily networks we started with, they look kind of pretty, we can measure their motifs, but the dynamics is kind of not really very well displayed in those sorts of networks. We'd like to have a better look at the dynamics directly. So instead of doing that, we chop up state space and we look at transitions between states. And this is where the parallel with Markov chains and Markov state processes comes in. So what I'm doing, here's my time series. I'm using 4 symbols here, but there is obviously a parameter, which is my window size. I take sequences of 4 points and I correspond them with an ordering. So here, that's the 4th largest, the 2nd largest, the largest, and the 3rd largest, 4, 2, 1, 3. The next window of 4 points, that's the 4th largest, 1st largest, 2nd largest, 3rd largest, 4, 1, 2, 3. Each of those permutations, 4, 2, 1, 3, 4, 1, 2, 3, and all the other permutations corresponds to a node on the network. So in the time series, you can visit the same node at different points in your time series more than once, but they're all nodes in the network, and I'm looking at transitions between those nodes. Right? So not only do I have a network where the network is not going to grow with the length of the time series, it's strictly a function of the window size and just sampling those different states that might occur. The network also now has probabilities associated both with the probability of being on a node and also the probability of edge transitions over the graph. That's just another picture of the same thing. So we take the time series, we perform this amplitude ranking, we take blocks of the time series, map them into sequences of points. Here it's shown us a little bit differently. So my original cartoon is hiding a lot of the complications because it looks like there's just one parameter, the window size. So this picture, which I've stolen from Michael, who's hiding somewhere on the call here, from Michael McCulloch, this shows the whole thing much better, but also shows all of the detail that I'm hiding. Here, he's got a window of 3, but he's got a lag of 2 between the components of that window, and the windows are overlapping as well. So the successor of the window that contains x of t plus 1, 3, and 5 is the window that contains x of 2, 4, and 6. Right? So there is some choices and some kind of embeddingness going on here that underlies the process, and it helps us determine how best to chop up state space. But at the end of the day, each of those permutations is associated with a node, here color-coded, and I'm glad that Thomas is actually hiding in another meeting and you can't see Michael's red, green, and blue points. But these are all different colors, and the numbers on the adjacency matrix correspond to whether we see a transition from green to blue or from blue to red. We could, of course, also think of it as being weighted by the probability of these things occurring. So, if we now take this idea and think about it in a slightly more formal sense, my ordinal sequences, each of those permutations of the integers 1 to w corresponds to a wedge in state space. The boundary between two wedges is where there's a tie between the two of the components in that permutation. So if I say there's a tie in the ordering of the permutation, that means that within that window of size w, there is an xi that's equal to xj. Right? So these are hyperplanes now through the origin, and so these are the boundaries between my different regions. So you imagine all the possible hyperplanes passing through the origin. They are chopping up state space into the wedges. Each wedge is a node on my network. We can think of each of those wedges as a label qi, and what am I saying there? Then these QIs partition our state space, and they intersect at boundaries. Well, the interiors don't intersect; they only intersect at boundaries when you get the ties. And so we can now think about our trajectory, which we could also write down like this. So our initial state z0, our trajectory is either forward mappings under the evolution operator of that, or backwards mappings. I've got a minus k there, that shouldn't be there. So obviously that should just be plus 2 kappa. So we get a sequence of these symbols, and we can think about the transition probability, which we are measuring on the time series just by counting up how often we see that transition. Well, that transition probability that we're measuring on the time series is exactly the measure of the intersection between these two objects. It's how often, if I'm in region J and I go backwards time kappa, do I end up in region I? Right, it's the intersection between all these wedges under the dynamics. So that's kind of cool, because it kind of suggests that the network is going to have the dynamics in it in some more interesting way. And indeed, this is true. So we can start to measure these various versions of entropy on the network. And essentially, these are all just p log p-ish properties. Topological entropy is a bit more complicated. I'll skip that for the time being, except to say that there's that we can measure topological entropy, and we can measure it from the properties of the Laplacian of the matrix, but I'm not going to talk about that Instead, I'm just going to look at these states pi and transitions between these states. So these are all the different states that occur. Transitions between these states defined by this p log p term as a entropy, either permutation entropy, which is per symbol, sum over the symbols, or conditional permutation entropy, which is the transitions that we're talking about here, going from one to another. Right, so it's, if I'm in a particular state, xi, and I go to some other state, where's my other state? Probably being in one state pi and then going to xi after kappa. Yeah, that's right. So permutation entropy is an entropy measured over the probability of each of the nodes occurring. Conditional permutation entropy is an entropy measured over the probability of transition over a particular edge for kappa equals 1. And if we look at some of these graphs, well, obviously, with what I've been talking about so far, if I've got periodic dynamics, then you'd expect a periodic chain of states on your network. This is complicated a little bit by the fact that if you have a smooth flow, and what you're measuring is, remember, it's the ordering of the points. So if your window W is in a region where you're just all going up, then that ordering doesn't change until you get over the top of your period, and then it starts to change, goes through a sequence of different permutations, and then you're always going down. So you're always at the same ordering again until you get to the bottom. Right, so it's not, the transition property is a bit more complicated. And then if you have noise, or you have W's longer, or you have embedding lag to worry about, you can get kind of, even with periodic situations, which all of these are, you can get much more complicated, more interesting patterns out, even before we start to think about chaotic dynamics. So whilst the theory looks good, the fact that we can write this down formally looks kind of nice, we are kind of opening up a can of worms here. These periodic ones already start to look a lot more complicated than these sorts of pictures we were getting out with the recurrence networks at the start. But we can still measure interesting properties. And so here, just for the very simple case of the logistic map, I'm computing the log of the nullity of the adjacency matrix here, shown as the red line, showing increasing as the chaotic dynamics becomes larger, Laplace exponent becomes more positive, and in the periodic windows, it's dropping down to 0. But this is the logistic map. Whenever you invent a new method in nonlinear time series analysis, the first thing you do is you test it on a logistic map. You show a picture like this with a bifurcation diagram and some wiggly line moving as the bifurcation diagram changes, and you celebrate because you've managed to diagnose something that you could pretty much guess by doing a delay 1 embedding of a one-dimensional of the map that you started with. All right, so it's necessary to show that things work on the logistic map. It's not particularly surprising to get things to work on the logistic map. So we should try it on the Henon map as well. So it also works there. That's good. That's 2 maps down. The Henon map is good because it's slightly more complicated. It's got 2 components rather than 1. And it's a little bit more exotic, but it's still not terribly surprising. But the Aikido map is a bit more complicated again. Still works. It's starting to show that it's under a bit of duress here in some regions, but it's still doing something. And we would like to think about something more than just entropy. Now, it turns out, and again, credit to Gary and others, that the largest Laplace exponent can be described in terms of the measures of the intersections of these intervals. Okay, so this is not so this is where we can start to see that maybe there's something interesting going on here, and there's properties that we would like to be able to estimate from the data. So we can do this. This isn't the picture I wanted to show. So this is for a small number of simple maps, estimating that maximum life exponent in exactly that way via different estimates of entropy versus the value that we expect to get out the red line. So the ordinal method, that's the network based on the method we just described in previous slides, performs best. Right? I'm getting closest to the actual value of life exponent. So that's all the toy examples over with. Now we ask ourselves, well, can we use this for some practical data for some real benefit? And so this is stuff that Michael McCulloch did with me, and I can see he's still on the line, so he can jump in and tell me if I'm talking crap at any point here. But we first of all looked at ECG time series of ventricular arrhythmia. So these are recordings of people heart rhythms, either in sinus rhythm, ventricular tachycardia, which is kind of, well, the easiest way to think about it is it's equivalent to heart flutter, but it's also a precursor to ventricular fibrillation. So if you've ever had that sensation where your heart's like palpitating because you just had a big surprise or something, that looks a lot like ventricular tachycardia. But it's also what happens before ventricular fibrillation sets in and you have a heart attack. We measure one of these entropies here with an embedding lag, which is depending on the original coordinate system, and an embedding dimension m, and we get 3 groups, which the distributions are different, but we can't distinguish between them. Right, so what that means is the distribution of the normal sinus rhythms, the purple triangles, and you can see that Michael's done more to appease Thomas than I did, and he's got different shape points as well as different colored points. So the triangles, the distribution of triangles are in a different place to the distribution of circles, to the distribution of squares, but in all of them, there is quite a bit of overlap between them. Right? So it's not something where we can clearly say, if it's bigger than 1, it must be normal sinus rhythm here, and if it's less than 1, it's not. There's too much overlap to distinguish between them, but the distributions themselves do appear to be different. But if we then try to use more than one of these things simultaneously, then we do start to see a difference here. So here I'm plotting 2 different, on the left panel, 2 different, and when I say I mean Michael. Michael's plotting here 2 different values of entropy with 2 different sets of embedding parameters, and looking at the distribution of these entropy measures for these networks constructed from these time series from these 3 different rhythms. There is still a bunch of points in the middle here where we can't distinguish between them, but aside from this bunch of points in the middle, we do see now a clear separation from area that's all green, all purple, or all blue. All the blue points are down here, all the purple points are up here. Why is this happening? Well, it's happening partly because more information is good. It's happening partly because if you think about what ECG looks like, ECG time series consists of slow changes and fast changes. Right? So there's some dynamics that occur quite slowly, and then there's that big peak that you see in a heartbeat. Right? So you've got like the slow repolarization, and then you've got rapid depolarization, and then repolarization again. Right? So you've got fast dynamics and slow dynamics that you're trying to capture at the same time. And by plotting this thing with these 2 different sets of coordinates, we are extracting information on different timescales. And you can then seek to statistically test whether these things are different and show that we are able to, with some reasonable significance, distinguish between these different states. Which again, it's a useful thing to be able to do, but it's not something that people haven't been able to do already. We are constructing a complicated method that allows us to distinguish between normal sinus rhythm and ventricular tachycardia and ventricular fibrillation. Everyone with an implantable pacemaker would be in a great deal of trouble if we didn't already have pretty robust ways of doing this already. second one, which we'll just talk about briefly, comes from one of the PhysioNet data sets. This is the so-called Fantasia data set, hence that's what Mickey Mouse is doing there. And essentially what this is recordings of RR intervals. So here we had the full ECG waveform. Here we've just got the peaks, right? So the time between successive heartbeats. And it's an experiment done in a laboratory where we're measuring ECG, not we, someone else. And you got a group of young people and a group of old people. The definition of old, unfortunately, I've recently moved from the category young to the category old. The definition of old is 40-something. So anyone over 40-something is old, anyone under 40-something is young. And it was done at a university, so one suspects that the young group were probably students, mostly in their 20s, and the old group were probably academics, mostly at least in their 40s. What they did is each of the subjects was put on an ECG machine, so measuring their heart rhythm, and told to watch the movie Fantasia. So this is just people's physiological response to watching Fantasia. And what we see is that young people and old people, well, I'll use the word react, but there's obviously a big question mark here, react differently to the movie Fantasia. There's no control here, so we're not necessarily saying that it's actually Fantasia. It might simply be that young people have different heart rhythms, whatever they're watching, than old people. It might not be that Mickey Mouse causes a different reaction in people under 45 compared to people over 45. But it's interesting that we can distinguish between these two groups, and the fact that we can distinguish between these two groups is about as good as anyone's been able to do on this data set. So this is kind of pushing it a bit further and showing that we can do something fairly robust and fairly decent with these types of methods. The next extension to this, and this is probably most relevant now for the work that we're trying to do in the ARC Maintenance Data Science Center. So this is EEG data. This is again from PhysioNet. This is epileptic seizure detection. So here you have EEG brainwaves prior to onset of a seizure. And we are doing the same sort of thing, constructing an ordinal network from little sliding windows of this, and then measuring some property of that ordinal network, and then looking at how that property varies over time leading up to the seizure. Now, for those of you that are listening that are part of the ARC, ITTC, Industrial Transformation Training Center on transforming maintenance through data science, don't think about epilepsy and EEG. Think about some big yellow truck that's going to blow a gasket up in the Pilbara somewhere, and we want to predict when to change that widget out, replace it with a new one before the truck breaks down. For the rest of the world, EEG is probably more interesting than big yellow trucks, so think about EEG. And what we're seeing here is variation as property that lead up to the seizure, and obviously when the seizure has started, we can see something different. And the question is whether or not we are able to, and when we stopped doing this, the question was, well, maybe, whether or not we're able to detect the onset of the seizure prior to the actual seizure being detected and scored in the data. Okay, so that I think is all I want to, pretty much what I want to talk about, except for two more extensions. One is all of this talk from the very start, I set this up as an experiment where I've got a time series and I'm measuring a scalar time series and reconstructing stuff from that scalar time series. We look at scalar time series because they are relatively easy, but very, very often we actually are able to measure more than one thing. So a natural extension is, well, what if we do have multiple channels? Can you get more information out with these sorts of measures if you have available to you more than one thing to measure? Right? We've been focusing on just measuring one thing over time because that's the easiest thing to think about. not because it's got the most information and not because it's what's likely to happen in the real world. So the obvious way to think about the extension to multi-channel stuff is, well, I've got here just 2 channels. I can construct an ordinal window for each of them. So here's my ordinal window for the black data. Here's my corresponding ordinal window for the red data. And now what I should probably do is each of these nodes on the network should be associated with a specific ordinal pattern in the first system and a specific ordinal pattern in the second system. All right, so there's W factorial of the first sort of thing and W factorial of the second sort of thing, and each node is choosing one of those things from each of those 2 groups. So this node here is saying that the first time series is in state 4213 and the second time series is in state 2143. Yeah. It then transitions to this other node where the first system is in this state and the second system, well, this time it has to be in the same state. So I've now got a network of transitions where the nodes are dependent on all the different channels of my system. Well, I just realized there's a big arrow in the middle of this picture. I don't know why that arrow is there. I must have got a bit excited when I was drawing the picture. Why could this be useful? Well, think about a system going into synchronization. In a system that's fully synchronized, phase lock synchronization, you're going to get the same ordinal sequence out of all of your symbols, even if you're measuring something different, or even if the sign is reversed and they're not exactly in phase and in the same direction, you're going to get one-to-one correspondence between the pair of symbols. So the network you're going to get out of doing this across all of your channels will be the same network that you'll get out of doing it from just one channel. In other words, the additional information that you get from building this network across multiple channels depends on, or another way of thinking about it loosely, the network you get out of doing this across all the channels divided by the network that you got out of doing it from one channel, that quotient is going to depend on how much more information is in those additional channels. So we could do the same thing that we described before, looking now at, I don't think the slide's saying anything much, it's just saying the same stuff as I said much earlier, but just saying on multi-channel. And so here we're doing exactly that for illustrating phase coherence of the transition from phase coherence to non-phase coherence for Russell system, and measuring again these entropy-like properties as we transition from phase coherence to non-phase coherence. Right, so you can see a change in the state of the system and a change in the measured output of the network, exactly as you would expect it at that transition. Okay, I'm going to try and wrap up in the next few minutes because I've been talking for too long and had an early breakfast, so I want an early lunch. This is the same sort of thing, and what am I showing here? The frequency of occurrence of each of my ordinal sequences over time. So you can see there's the different ordinal sequences that I'm allowing to happen and the frequency with which they occur. The entropy that I'm computing from that network, or those sequence of ordinal patterns. And the phase synchronization of my 3 oscillators. So here I've got 3 oscillators with different rotational frequency. 2 of them become locked, and then the third becomes locked here. So these change points are where the oscillators become locked, and at those change points, the entropy drops. Right? So again, exactly what I described by waving my hands back here is happening. As the oscillators in the different systems start doing the same thing, the network contracts and looks exactly like the network I get from each of those oscillators independently. And it's a smaller, simpler network. This, honestly, forgotten what I'm actually showing in this picture here. So this is showing exactly the same thing, except here I'm just showing my different nodes in my network. These are the different phi 1 to phi 8, and going through different phases of kappa from 0.2 to 0.8. So 0.2, 0.6, and 0.8. So that's 3 incoherent oscillators, 2 of them synchronized, the third not, and all 3 synchronized. So 3 incoherent, 2 synchronized, and in C, all synchronized. So you can see exactly the same. As the level of synchronization increases, you get this dominant cycle coming up, which is all that you will see when they're fully synchronized. Okay, so finally, and this is where I finished because there is no slide in between that and the end. This is, compression nets is what Dave and Deborah are promising to do with the sheep and deer and emus and alpacas and lions and all sorts of other animals that we heard about yesterday that we're collecting. Well, when I say we, I'm grateful that when I say we now, I mean someone else is collecting data from by implanting sensors in these animals. And compression nets are the same type of idea, except it's a different encoding of the states. And in a nutshell, if I can just summarize in 2 sentences, what we're planning to do here is, rather than create code words that map onto, rather than create code words that map onto nodes via these ordinal permutations, our code words will be code words that are constructed through impulsive Welsh compression. So I take, and here when I say I mean Deborah, we take a time series and you quantize it to different symbols just based on levels. So quantize your continuous, almost continuous time series to 4 levels or 8 levels. That gives you a sequence of symbols. And then apply an impulsive Welsh encoding to those sequence of symbols. So what LZW encoding is going to do, and in fact it's not impulsive Welsh, it's a impulsive Welsh-like algorithm, which we're calling the Walker impulsive Welsh algorithm. We applied this algorithm to this sequence of symbols, and what it does is sequences of symbols that occur more often are recognized as discrete code words, and they will come out of that encoding process. So our code words in our network are not individual states, but are collections of states that are occurring most frequently. So if in the symbol sequence we see a lot of AB, 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 then we encode that as a single symbol. Could be AB or it could be AB, AB, AB. We encode that as a single symbol representing that as a particular pattern we're seeing over and over again. So the nodes in the network are states that we are in, patterns that we are seeing occurring and recurring. Okay, so this is kind of work in progress. There is a couple of papers in IJBC and EPL, Deborah, is that right? Nod your head. Europhys letters or somewhere. We've got a couple of papers out on this stuff in the last year or so. Chaos. What's Chaos? Well, oh, that journal. I've heard of that. So one in Chaos and one in IJBC on doing exactly the sort of process. Okay, so finally I will stop. I didn't get to talk about Costas's new work, and this is a perfect excuse, Deborah, to get Costas to come and talk about it with us if he's not going to talk about his other stuff on one of the Thursday meetings. Got plenty of things for him to talk about. The main references from which this is everything I've talked about comes from is Costas and Michael's PhD theses, both of which are incredibly well written, and I thoroughly recommend them, and you should all read them because they're good. If you don't want to read them, there's a 4-page paper here where we did some of the stuff early on, and there's a sequel to this which is much better written, which Michael wrote in ISCIS in 2019 maybe? 2018, I think. Summarizing in 4 pages everything they did in 4 years each. Okay, I'm going to stop. Oh, and the philosophical transaction paper is all the application stuff that I was talking about at the end, which is all Michael's work. And there's some other stuff which I didn't talk about, which is also interesting, which is why Thomas wanted a credit, and that is looking at specifically how these forbidden sequences start to occur as a function of irregular sampling and undersampling of your time series. Okay, And all these people did the work, and I took all the credit. So any questions, anyone?
Hello, Michael. Fabian here.
Fabian, hi.
Hi. So my question is, how much the performance of the classification of the ECG data would be impacted if your sampling change? So like where I'm going is I kind of assume that your sampling is well adapted in the sense that the pattern you see, well, they are like 4 letters, right? So you kind of got lucky, and these 4 letters capture the dynamic of the pattern. So how do you do if, well, you don't have the right sampling and you need to kind of fit your Ordinal network to, well, to find a more efficient pattern?
Yep. So sampling is always a problem. Especially so. This goes right back to the very first slide where I was talking about Tarkin's embedding theorem. And there's a mathematical theorem. It proves this can be done. Well, Tarkin's theorem doesn't. The network stuff, not so much. There's a theorem that proves it can be done, but that doesn't tell you what the best way to do it is. And the same thing is equally true of the network stuff and the ordinal stuff. We still need a good way of representing those states, and it's always possible that we can do it in a dumb way and get bad results. Second issue, so a lot of it, or as well I should say, some of it we can compensate for by clever sampling. So for example, with this, in this example here, we're using 2 different time lags, 2 different samplings essentially, so that the information we get out is somehow most useful to us. If we just chose any particular embedding dimension, embedding lag, some of these do particularly poorly and wouldn't be a good choice.
All right. And so how do you pick these 2 time lags? Like, is that?
So I'll get to that. I want to, one more thing before I answer that question. Okay. The other thing is, so these are situations where we have that choice. Sometimes we don't even have that choice. So some of the stuff that we're working on now with the mining industry, the data is so poorly sampled or poorly quantized. You don't even, you really want them to be there to be more data because the sampling is just bad. But assuming the sampling is good enough, then there is methods with varying levels of heuristicness in them that we apply. The general principle is that as you add new components, you want to add more information to your construction. And you want to create a construction with as much information as possible. You want to construct with as much information as possible, but you also want to try to keep that information correlated. So if I want to get as much information as possible, I just wait a very long time. But then those 2 states are completely different, that I've got as much information as possible, but it's information about 2 different things. Right, so I want as much information as possible, but I want to take it over a short time so that additional information is information about the same thing. Now, when we're constructing these networks, if you think about this for a moment, that kind of put a network picture up, we're essentially looking for, well, we're essentially looking for 2 sorts of things here. We want to, if we increase our window size, just think about that single parameter, we increase our window size, that means the network's going to be larger, means there's going to be more nodes, means there's going to be more transitions, means there's going to be more information about transitions. But I've got to estimate more things. So as I make that window larger and larger, I've got more states to estimate. But if my time series is not big enough to cope with all of that, then my estimates are going to get worse. So there's kind of a trade-off between having a larger window, and if your window is too large, you're trying to estimate too many things. So it's a purely statistical estimation problem here of, I want to estimate as many states and state transitions as I can reliably. So in terms of actually estimate, in practice, how do we do this? we use things like mutual information, autocorrelation, a quarter of the period of the signal, all the usual things that people use for time delay embedding give us information about what the best way to choose these lags are here as well.
Gotcha. Okay.
So there was a question, is it effectively a Nyquist frequency for the motif? So, so Paul, you mean way back at the beginning? Is that what you mean? This stuff?
Sorry, I was trying to find the unmute button. Yeah, I mean, I guess it's sort of related to the last question as well.
Yeah.
So, like, is there a Nyquist type frequency in relation to what information is extractable out of the time series? Like in typical Fourier analysis, we have this concept if we can't resolve a signal if we don't have enough points in the sequence.
Yeah. So the it's connected to the last question in the sense of the last thing I said about if I'm trying to estimate more states, I need more time series to estimate them. There's a sort of probabilistic connection between being able to estimate a number of states. As that number of states grows, I need more data to feed in to get good estimates. That's not exactly the same thing as a Nyquist type limit, though. There is a Nyquist type thing going on here in a couple of ways. One is in exactly the same way as a Nyquist limit, you can't distinguish chaos from periodic orbit unless you see enough of your signal, right? So with the Nyquist limit, you can only resolve up to you need 2 points or more per orbit, per cycle to get information out of it. If I've only observed one cycle, I don't know whether it's chaotic or periodic.
Mm-hmm. Yeah,
that's kind of the Nyquist idea in this sense here, I think. Is that what you're getting at?
Yeah, I guess it was. Yeah, that makes sense. I have a follow-on question if no one else does as well. So I'm from the Ocean Graduate School. Thanks for letting me crash your lecture.
No problem.
So ocean model data is often stored as compressed binary chunks where space and time is sort of partitioned in order to make access to the data efficient from a sort of compute perspective, because there's a lot of information. But it seems to suggest to me here that potentially we don't need to decompress that data in order to extract patterns in the compressed information, because there'll be recurrence in the compression algorithm. Is that what you were suggesting in these compression networks?
So I flicked forward to the compression network because I thought that was what you're going to ask me, and then you asked me something slightly different at the end. So let me answer the question I thought you were going to ask first. So when we were talking about the compression nets, this is exactly the type of situation we were thinking of, where you've got masses of data, and this data may be being collected at a remote site, and you want to be able to have some way of downloading it, dealing with it, and measuring it without all the issues of dealing with gigabytes of data that you're trying to get off the Northwest Shelf. And so the compression nets idea was an idea to try to get the most information in an efficient way and send that. So yes, that's kind of what we're doing here. And that's the objective of this work. And because with the work that Dominique is doing with the sheep and the deer and the emus and stuff, it's the same sort of problem in that they've got masses of data and they don't want to have to stick a hard drive on every emu to download it all. They want to kind of get some lower volume of data from the sensors. Now, there's a separate question that you touched on when you talked about recurrences being the key thing. That is exactly right for a lot of the low-dimensional chaotic systems. The recurrences encode all the important information about the system, and you don't need to know everything about the cycles. A simple way of thinking about that, especially for the students that I hope are still on the line, if you look at a Poincaré section, a first return map of a dynamical system, what you're doing there is you simply look at intersections of your long-term dynamics with a particular surface in your state space. Another way of saying that is just look at the peaks. And if you just look at the sequence of peaks, that tells you everything you need to know about the dynamics to know everything else that's going on as well. So there is information efficiency that could be obtained by using these recurrence ideas on the sort of data that you describe.
Thank you.
Any other questions, anyone? Just for Braden, Eugene, and Alex, I think Alex is still there. Yeah, Braden, Eugene, and Alex. If you guys have questions about the unit and the assignment and stuff, send me an email or contact me in Slack, and we'll set up a time either today or through the weekend or early next week to go through that. Does anyone else have any questions about the talk?
Is it due on Monday?
Yeah, but whenever. Sometime next week would be good, Eugene.
Nice, I like that.
I assume that because I've told you it's due Monday that you've done most of it now already, so it's not going to be an issue, right? Yeah, so look, it does mean that you've thought about the questions by now, so email me or communicate as a group through Slack, and we'll set up, we'll see how much needs to be done between now and whenever. And if there's no more questions, okay, Eugene's happy. Any other questions, anyone else? Well, if not, thank you all for turning up. I hope you hung in there and enjoyed it and got something out of it. Made a change for me from just talking to 4 fourth-year students. And I think all that remains is for me to advertise. Who's talking next? Oh, it's me. Complex System Seminar next week will be me speaking again about, this is next Thursday at 3, and I'll be talking about modeling coronavirus transmission with networks. So until then, thank you all for turning up and have a good weekend.
Michael.